Okay, so today I'm going to cover electrostatics. So electrostatics is a term that we use to describe the effect that different charges have on each other, different charged particles have on each other, and different charged objects have on each other. So the first thing we need to establish is what on earth is a charge and what on earth is a charged object. So if we look on the inside of an atom, then we have protons, neutrons, and electrons. Neutrons are neutral, they don't have any charge. And protons and electrons are charged. Protons have a positive charge and electrons have a negative charge. And besides that, protons sit in the center of the atom and electrons move around it. So if we look at the terms of what we term an object that is positively charged or an object that is negatively charged, what we're actually meaning is that this object, for some reason, has fewer electrons than it's supposed to have for a positively charged object, and more electrons than it's supposed to have for a negatively charged object. We can have the same happen with a single atom. So if we get a single atom that has some positive charged particles, so some protons in its center and some electrons going around it, and we then get some more electrons that come in and attach itself to this atom, we have what is termed an ion. Okay, so we have what is termed an ion. Ions are literally charged atoms, if I can put it that way. So if we have a negatively charged atom, then we have more electrons than the atom is technically supposed to have. So a normal helium atom is supposed to have 2 protons in its center and 2 electrons floating around it. But if there are 3 electrons, then the whole thing has a net negative charge, because the 2 positives and 2 negatives that it's supposed to have sort of cancel each other out, and then we end up with this extra electron that gives it a bit of a negative charge. So with a positively charged atom, what that means is that this atom has lost one of its electrons, or a few of its electrons even. So what happened is, due to something, it could be friction, it could be other forces or anything, that electron has been given off by this atom. Which means that now this atom has one or 2 fewer electrons than it's supposed to have, and that in turn gives the whole atom a net positive charge, because not all of its electrons and protons cancel out anymore in terms of its charge. They now have more positive protons than it has negative electrons. So it has a positive charge overall. Okay, there is a question about the science exams. Science exams are at the end of your subscription, so you don't need to worry about it too much. Once you have finished all of your assignments, your teacher will contact you and ask you about when you want to write the exams and how. Okay, don't worry about exams. Okay, so we have atoms that can be positively or negatively charged, and we also have objects that can be positively or negatively charged using the same principle. Somehow this object has more electrons than it's supposed to have, or the object has less electrons than it's supposed to have. So if it has more electrons, then it's negatively charged, and less electrons, it's positively charged. Okay, so we represent these sort of charged things using either a plus or a minus inside a little circle. So I am going to show you that quickly. Once the share works, there we go. So Okay, so if we have a positively charged atom, we can put one over there. So I will put all of these links that I'm going to use today in the chat so you guys have it, because it's lots of fun to go play around with all of these simulators. So if you have a positively charged atom over here, then this is sort of what its field lines will look like. The field lines I'm referring to here is the same as if it was for a magnet, where you would have a north pole or a south pole, except now you don't have a north pole and a south pole as for a normal magnet. What you now have is just one pole. You've got the sort of positive pole here. Now, if we go and add in a negative charge over here, this is what will happen. So they tend to attract we call these field lines. So just as if the field lines would move from a north pole to a south pole in the magnet or for a magnet, we get the same thing here. It'll move from positive to negative in terms of the charged particles. This is a convention we use in terms of these things. Okay, an atom, I just had a question here. An atom becomes negatively or positively charged by losing electrons. So if it has the normal amount of electrons it's supposed to have, then say for a helium atom, 2 protons in its center and 2 electrons floating around, then it's neutral, because the 2 positive charges and the 2 negative charges cancel each other out. However, if for some reason it has lost an electron, then it will be positively charged. So it has, say, 2 positive atoms on the inside and 1 electron around it, then it'll be slightly positively charged, because those two, the 1 proton and the 1 electron, will still cancel each other out in terms of charges, but then you'd have this 1 charge left. Same thing for if it picked up an extra electron. Okay, so another question, how can an atom lose or gain electrons? This normally happens using something like friction, or even electric forces can sometimes be used in order to have objects lose or gain electrons. So the one that you guys have to worry about is friction. So how the friction one works, I'm just gonna stop this so you can see me. How friction one works is you have 2 kinds of objects that will be rubbing up against each other. And at an atomic level, that is literally the atoms sort of rubbing up close to each other. At some point, the orbitals of the electrons can overlap, and then that electron can transfer from one atom to another using this sort of friction. This is what you get when you have static electricity. If you have ever walked across a very plush carpeted floor and then touched the doorknob and shocked yourself, that is static electricity. If in the winter you have tried to brush your hair and your hair has suddenly decided to stand on end in 10 directions, then that is static electricity. What that meant is, for some reason, and it's normally the air is dry and there is lots of friction involved, that's when you end up with static electricity building up. I will show you a Van de Graaff generator a little later in order to show you how this whole thing works. So getting back to our single charges, here we go. So we have a single positively charged atom over here and a single negatively charged atom. And we can see more or less how these field lines work. Okay, so I'm going to put a sensor here. So a sensor in this simulation isn't actually a physical thing that we can go put there to measure. This is a sort of imaginary way that we can see these. And it's just to show you that the closer you get to an object, the bigger the force that object will exert on it. So the closer we get to the positively charged atom over here, the bigger the force this atom will exert on it. So if we move very far away, then the force will be almost nothing. If we move very close towards this negatively charged one, then the force will be high again. And the direction of this arrow, so the length of this arrow shows the sort of amount of force, and the direction of this arrow just shows the direction of the field lines. So there it sort of lines up with that arrow. Okay. So if we have a positive and a negative, this is pretty much what a magnet would look like. So with, say, a north pole and a south pole. But now, if we take this away and we add in 2 positive ones, then we get this strange sort of reaction over here. So what happens here is that the field lines on the inside over here would be pointing away from each other. So I'm going to show you a different simulation where you can see that much better. So in this simulation, if you want a charge of 2, you can't really just make the charge 2. You actually have to go put 2 of them on top of each other in order to see what that looks like. But you can go and play around with the simulation as much as you'd like. So I am going to show you guys, here we go. So if it is, here we've got an electric field line simulator. I will post the links so you can see this and go play around with it. So here we can see the field lines that they make. So if we have a single charge that is positive and a single charge that is negative, this is what the field lines look like. And this is pretty much exactly what you would get in terms of an electron, a magnet. This is your situation. That would be the north pole of the magnet, and that would be the south pole of the magnet. Now, if we change these charges and we make the one stronger than the other, this is what the field lines would look like. And again, continuing on until this one you can see is very, very strong. This one is a lot weaker. So now, this is if we have one neutral and one that actually has a charge. That neutral particle will have pretty much no effect on it. Now, if we have 2 particles that have the same charge, then we end up with a situation where the field lines are not crossing and sort of has this gap in between. So this is what that looks like when we've got 2 charges that are the same. So if we make the one stronger, then as you can see here, it would sort of push the field lines away for the other one. So I will put this in the chat and you can go and play around with it. You are most welcome to. So I've gone through this one and this one. So again, this is single charges. So here, this is another simulator. What this one has, which is kind of cool, so we can have field lines. So if we tick the field line button, then it'll start drawing in different field lines. It plots them one by one, hence why it looks like this. In real life, it doesn't just start one by one. It's just the way that the simulation works. Okay, so this is how it would look if we have lots of field lines. So if we have a single charge, that's what we'd have. We can change the charge size over here. So how much charge it has. This would mean it has lost 3 electrons. So it is 3 plus. So it's got 3 extra protons sort of to give it charge. If we have a dipole, this is exactly what a magnet would look like. It would have a north pole and a south pole. So a dipole here would be something that has the exact same charge on both sides, a positive and a negative. Here, if we add in some field lines, you can see what it would look like if you had lots of different charges and things. We can even move these around clear it up and then add in the field lines again. So you can see what all of these different configurations have. So you are most welcome to go play around with it. It is remarkably fun to play around with. This is what it would look like if you just had a big row of these. And this is a dipole row. And this should start looking slightly more like you would suspect a magnet would. Okay. So I'm going to show you guys these. You are welcome to play along with them. So for now, I'm going to show you guys a Van de Graaff generator. So here we have a video that I'm going to show you. A Van de Graaff generator is a way of making lots of static electricity. So he explains it fairly well.
Generator demonstrations.
So here we go.
Explain how they work too. So here's the inside scoop. The thing that all these demonstrations.
This I think is done in work 17. There's a question about what week this is handled. It's either week 17 or week 27. I will get back to you in a second. But please watch the video in the meantime.
In common is that they interact with the top dome. So let's see what's going on there first. The top dome of a Van de Graaff generator is either positively charged or negatively charged. That means it either has more protons and electrons, making it positively charged, or more electrons and protons, making it negatively charged. The key point is that it's kept that way. If we add some electrons to a positive dome, by arcing to it, for example, that makes it less positive. But those electrons are quickly pulled away from the dome, and the dome is back to being positive again. The same is true if we were taking electrons from a negative dome. New electrons are quickly put back on it to make it negative again. There's an endless supply of charge, and it's constantly being replenished. Now on with the demonstrations. I'll start with this well-known hair-raising demonstration. Now my hair isn't long enough for it, so I'm going to put on this collection or crown of strings on my head instead. Start with the Van de Graaff generator turned off and not charged up. That's so that you don't get a shock when you first touch it. Next, stand on an electrically insulating platform. I'm wearing rubber-soled sneakers with the laces tucked away so they don't touch the ground. That's good enough. Next, put your hand on the dome. Then turn on the Van de Graaff generator. Your hair should now raise up. Give your head a shake to help separate the strands of hair. When done, you can remove your hand, as long as you're still insulated from the ground. I discharge myself by touching a wire connected to the ground, getting a small shock. I then turn the Van de Graaff generator off, still keeping myself away from it in case of a shock. Then I bring the end of the ground wire near the dome and touch it. It's now safe.
Touching a Van de Graaff generator with a grounded wire or something that is grounded is called neutralizing it, so that you can sort of reset it and then start again.
So how does this work? Your skin is not a great electrical conductor, but it does conduct some electricity. Since you're touching the dome, you're basically a part of it. If the dome is positively charged, then you become positively charged. Electrons are taken away from you and your hair by the Van de Graaff generator. That means your hair now has more protons than electrons. It's positively charged. The important principle that makes your hair rise is that like charges repel each other. So each positively charged strand of hair repels each other positively charged strand of hair. They try to repel as far away from each other as they can. But a clump of hair stuck together can act as one. Shaking your hair separates the strands so that they can act individually and repel each other. In this demonstration, a stack of metal pie plates fly off one by one. How does that work? Well, the outer surface of the stack becomes charged, not all parts of the plates at once. That's all the visible surface of the top plate and the visible edges of all the other plates. That's due to the Faraday cage or Faraday ice pail effect. Notice that just as with the hair, the plates are charged the same as the dome, positive in this case. Only the top plate is free to move since it's on top, and the edges of the top plate and the plate below it repel each other. Remember, like charges repel. As the first one rises, the newly exposed surface of the second one becomes charged too and repels the top plate more strongly. The top plate is repelled away. Anyway, now we have a new top plate and the whole process repeats. This demonstration consists of my crown of strings in direct contact with the top of the Van de Graaff. When the Van de Graaff is turned on, the strings rise and separate, just as your hair did for the very same reasons. Here a bunch of strands of toilet paper are taped to the dome instead. You don't need a big Van de Graaff generator to do demonstrations like this. Here's a small homemade.
Okay, there we go. He goes on to explain how he has made his own little Van de Graaff generators using some cans and some other bits and pieces that you have around the house. So you are most welcome to go look at those. Just please be careful and practice safety. I will post the links in the chat soon. So a Van de Graaff generator is a generator that generates static electricity. The way it works is it's got a brush in the bottom part of the generator. It's got that big long tube and then the top dome. In the bottom part, there is a little brush that would continuously rub against this band of, it's normally a rubber band running around. And that would in turn actually charge this band using either electrons or protons, depending upon what exactly the Van de Graaff generator is made out of. So that generates lots of static electricity. You can generate lots of static electricity by running around on a fluffy carpet in the winter. That generates tons of static electricity. The other ways of generating static electricity is if you take a balloon and rub it up against your hair, that would generate static electricity, and then you can use the balloon to pick up little pieces of paper and all sorts of things. So there are lots of experiments you can do using static electricity. And that is essentially what this whole lesson was about. So let me quickly post all those links for you guys. Okay. I'm going to share my screen so you know what I'm doing as I'm doing it. So firstly, here we go. There's the YouTube video. Okay, this is the electric field line simulator from Academo. Here we have this charge simulator. Some of these do require Java in your browser, so be aware of that. Here we go. Here's the Flash Physics one. And then lastly, I want to show you guys this website. It has lots of very short, tiny videos about lots of scientific topics. So if you look over here, this one talks about electric force and how that works. Coulomb's law. So what Coulomb's law states is that like charges will repel each other and unlike charges will attract each other. So if you have a positive and a negatively charged object, then they will attract each other. And if you have a positive and a positive, then they will repel. So you can look at all of these. There's the electroscope that is talked about in your lesson on CambriLearn. Here's a bit about how static electricity works, how the charges sort of move around. And you can go play around with all of these up to about electric field and potential. These are topics for a different lesson. So let me go put that in the chat as well. There you go. Okay. That is pretty much the end of today's lesson. Do you have any questions about this so far? I know there's a question about what week it is. 2 electrons will not attract each other. 2 electrons repel each other. If you recall, last week I believe I did the lesson on atoms. And then when I drew an atom, I would put an electron at the top, and then the next electron would be at the bottom. And so you sort of draw them like that. And the reason for that is exactly that electrons repel each other. They like to be as far away from each other as possible. So yes, 2 electrons will repel each other, as will two positively charged atoms, two negatively charged atoms, two self poles of magnets, and so forth.